Hello students, so in this lecture we will be discussing about nano-bio Now nano-bio are sensors which are mainly used for biological sensing or biomedical sensing. They are used for mainly for controlled drug release, then cancer detection, then detection of blood sugar, biotoxin. There may be some specific DNA which needs to be detected, and there may be some chromosomal defect which needs to be identified. So all these aspects can be dealt with nanobiosensors. Now, one of the most common uh, nanobiosensor is in the shape of a cantilever. Like this is a cantilever, and its shape is also, we can say, a micro regime, but it actually captures cancerous cells which are in the nano regime. So we can say that cancerous cells, cancer cells cell growth, and these are mainly nanograms. Now, if you look at the shape of a cantilever, it has a fixed end, as given here. It has a fixed end, and it has end which fluctuates or bends. So this is the bending end. So this is mainly, first it is the base is always silicon, and then it is gold coated, and the gold coating is on the top. Now, to this gold coating, there are some antibodies which are again coated. The reason of coating this antibody is again is to bind the prostate specific antigen responsible for the cancer and found in blood. In short, it is called PSA, prostate specific agent. So it gets attached to the coated antigen antibodies, and then it as it attaches, there is a change in mass, and it starts to bend or vibrate. So through this we can actually find out that the growth, we can monitor the growth, and we can assess the growth. Now the same principle can also be used in making a nanomechanical microcantilever based upon piezoelectric effect, where a resonant frequency shift is based upon which the sensing is done. So initially there is a shift in resonance, that is, if there is an LC circuit, then 1 by 2 pi root LC. If it is an LC circuit, then this is the resonant frequency. So if there is a shift in frequency due to this absorption, then in a piezoelectric based nanomechanical sensor we can detect the material that has, or the cancerous cell that has attached with the antibody. Now these microcantilever, based upon this microcantilever, various biochips are also formed. These biochips, there again, they also detect various biotoxin like anthrax, aflatoxin, and etc. and these toxins are released for biological warfare. So if we have a biochips installed, we can detect it and prevent these sort of biological warfares. The next aspect about these cantilever sensors is the sensitivity aspect, or uniform mass sensitivity. Now, what we can see here is, if this is a adherent which is getting attached to a sensor, it has the option to get attach itself in any along the length. It can attach at the edge, or it can attach at the clamping end. Now this position of this antibody getting adhered, or this adherent position, it greatly affects what kind of vibrations the cantilever will experience. If it is at the edge, namely this is how it will have the maximum vibrations, and if it as it moves closer to the fixed end, the vibrations decrease. So there is an non-uniformity in the vibrations that we receive. So to maintain, to create a uniform distribution, mass distribution, or rather uniform assessment, not depending upon the location of the sensor, location of the antibody getting adhered, a change in design was done. And the change in design, as you can see, it came in the form of a fourth clamped sensor called a pedestal cantilever. So we had one clamp previously, it was only one, but we have now four clamped, 2, 3, and 4. So the advantage this sensor has, if wherever the adherent sits, the sensitivity is not compromised to that extent as it was in the case of a one clamped sensor. So it provides uniform sensitivity. Now mathematically, this vibrating pedestal cantilever system can be expressed through a modeling by a spring mass damper system. So it's as if that is a mass connected to a spring, and associated with this is the capacitance. Now two numbers are used. One has been used for the cantilever, that is the bottom one, and the top one is used for the adherent. Now the factors which govern the oscillations are the mass, the spring constant, the damper, and the oscillation, vertical oscillations themselves. These factors determine what kind of oscillations that we are going to get. So this they provide, we call the oscillating frequency of the cantilever. Now, in this case, if there is an adherent, okay. Now another way. Now this whole system can also be put in the form of an equation. So we can see that if omega is the oscillating frequency, which has been explained previously, and if it's the force applied, so this can be put into an equation where the first term represents the mass that is getting adhered. The second one is the damping system. This is the spring system. And at fourth, we have the force, and correspondingly, you have the oscillating force, the frequency with which a frequency is attached. Now, let's say you have a pedestal cantilever like this. Now, to this pedestal cantilever, our next, if we allowed a film, if we assign a film, the antibody film to capture the PSA. Now, deposition of the film is equivalent to having an extra capacitance in parallel with the capacitance C1. So this is basically the cantilever part. This is the cantilever part. So to this an extra film has been associated. And now what will this do is will change the parameters a bit. It will enhance the spring constant. So the spring constant, which was K1 for a cantilever, now it gets increased by delta K, and CS here E stands for the compressive stress. So we are assuming that a compressive stress has formed due to the deposition of the film, which is enhancing the spring constant. However, it does opposite to the damping part. So the damping part, since it is arranged in parallel, it gets reduced. So we have a delta C compressive stress also. So the dampness gets reduced and the oscillations or the spring constant, they get enhanced. Now the film that is deposited here, it might have some defects, or it might have some cracks or whatever you may call it. So for that the upper section gets modified. Like in the previous case, we have an extra C, delta C TS getting attached with the upper system. So in this case, the capacitance, like the previous one, the C2 capacitance will now be affected by this delta C TS. TS stands for tensile stress. So the oscillations, this is how the oscillations will change, because there will be a change in equations. This C1 and C2 and this K1 and K2, they will no longer hold, and neither will this frequency. Okay, so that's how this oscillation, which is the resonant oscillation, will change to oscillation due to a compressive stress CS, and or oscillations due to tensile stress TS. So this is the mathematical aspect of the frequency change. Now this frequency change, as told previously, gets detected by a piezoelectric sensor, which gives the response in terms of change in current, or it can also get affected. It can also be detected by using a laser light, like in the case of an AFM, where if you have a laser pointed at this surface where the film position and adherence are getting captured, so these vibrations will cause a change in the reflected laser, which gets monitored through a photodiode on a screen. So we can observe the different vibrations, and we can detect the sensing. So this is what the nano-bio sensor is.